Today, we're going to learn how to run a chi-square test by hand. Last semester, we looked at the t-test. The t-test is used to compare the means of two different populations and see if they're different. To do this, we calculate the variance, compare the means and the variance. The t-test can only be done on measured data because we need numbers that we can then find an average and a variance of. But not all numbers we collect, not all data we collect is measurable. A lot of the data we collect is counted. So when we are trying to compare the two populations where data is counted, then we're going to look at how many data points we observed versus how many we expected to see. And that's what we're going to learn how to do today. So t-test is a parametric statistic. We're looking at measured data. Chi-squared is a non-parametric statistic. We're looking at counted data. This is the chi-squared equation. It's way easier than the t-test. We have the symbol chi-squared. This is not a number that we're going to be square rooting. This is the symbol. We are trying to find chi-squared. Chi is this squiggly x, sometimes written like this, sometimes written like this. A squiggly x is chi. The symbol chi-squared is what we're looking for. We're not trying to square root it. We don't want to find plain chi. This lovely symbol, sigma, means the sum of. It means we're going to take this part and add it to itself over and over again. So the only things we need to do is we need to find our observed numbers, and then we need to calculate our expected number. Like when we did t-test, we had to calculate variance before we could run the t-test. But to find the expected is a lot simpler. Now, I was trying to figure out what data I wanted to look at, and then I remembered my butterflies on the wall. So here is two of the pages from my Butterflies of North America. This chart is all of the butterfly species of North America at the time that this book was published, which was the 90s. So it's a little bit different now, but this is what we're going to go with. So these two pages are all of the butterfly species found in Western North America. Now what we want to do is we need something to compare. So we're going to compare how many orange butterflies there are versus how many white. Step one, we need to write a null hypothesis. You remember from doing the t-test? The null hypothesis. We're always assuming everything is the same. There is no difference. When I do this as a class, I usually have this as a clicker question and get people to choose which one is correct. So we want the one that says there is no difference. So not this one. And we want the one that is the most specific. The difference in the number of species of orange butterflies versus the number of species of white butterflies on the West Coast North America. The number of orange butterflies versus the number of white. So this one is specifying the number of species. So this is the one we want. Now, in biology, null hypothesis is all we use. We simply write down a null and then we reject or accept our null hypothesis. But many of you taking the first year environmental science class, you're not biologists. And in other disciplines, they do something called an alternate hypothesis. So we're going to learn about it. We don't use it in biology very often, but it is something good to know about. The alternate hypothesis is basically the opposite of the null. So we know that this one is the null. So which one's the opposite? There is no difference. There is a difference. A for alternate. So it's this one, not this one, not this one. Ta-da! So that's how I remember this. I remember no, null, a, alternate. There is no difference, there is a difference. When we're doing chi-squared, I find it simplest to make a table. So I want to record all of my observed numbers. I like to record it into a table that makes it easy for me to know what I'm recording and then easy to put my expected values in later. So here I have my categories, which is color, orange and white, and I have my observed numbers and my expected numbers sharing a column. So we're going to see why this is a dotted line in a little bit. But first, let's count our orange and our white butterflies. This is step 4. We just have to count. When you were doing your own research, for example, with my salamander research, it took me months and months to count all my salamanders doing their behaviors. Today, this is going to be fast. You're going to have to trust me that these are the orange butterflies. I know the colors aren't great on here, just the lighting in my office, but these are the orange ones. And we could have arguments about which ones are the orange ones and which ones aren't, but for now, we're going to go with these. This guy is, in my opinion, half orange and half white, so I'm not going to count this particular butterfly. I'm just going to count the others. So that gives me 18 orange butterflies. Here are my white butterflies. And yes, some of them aren't all white or perfectly white, but these are the ones that I'm going to count as white butterflies. They're mostly white. White is their dominant color. These are 14 white butterflies. If we put those into our table, it looks like this. Now we need to find those expected numbers. The calculation for this is the total divided by the number of categories. This is because we're assuming our null hypothesis is correct. We made a null hypothesis. There is no difference. Everything is the same. That is the baseline assumption in biology. We're trying to prove that something is interesting, that something is different. So if everything is the same, if there is no difference, our expected is that the number of butterflies is divided evenly between the colors. So our total divided by the number of categories. So here, our total is 32 divided by the number of categories, and we get 16. So this is where it's important to see that this line is dotted because 16 and 16 equals 32. This is all one column. The observed and the expected are sharing a column. Understanding that the observed and expected share a column becomes more important when we go to the next step. But for now, I just want you guys to be aware of that. So we've got our observed numbers. We've got our expected numbers. Now we just have to do the math. Step 6, find calculated chi-squared. So how we do this is chi-squared equals the sum of. So we're going to take this part of the formula and add it to itself. So observed minus expected squared over expected plus, that's what the sum of means, observed minus expected squared over expected. How many times do we add it to itself? We add it to itself for the number of categories. So only 2. We only have 2 pairs of numbers, 18 and 16 and 14 and 16. So we only need to add it together twice. So then we just plug in our numbers. 18 minus 16 squared. Oh, 14 minus 16 squared. So 18 minus 16 is pretty easy math. We've got 2 squared over 16. And 14 minus 16 is negative 2 squared over 16. This is really common where our numerators are paired, positive and negative. We'll see this again probably. 2 squared equals 4 over 16. I'm going to bring this up here. The great thing, the reason why this squaring is here is to get rid of this negative number. Mathematicians don't like to have negative numbers. So we frequently see situations where they square numbers to make everything positive. 4 divided by 16 is 0.25. So chi squared equals 0.5. This is our calculated chi squared. Calculated chi squared equals 0.5. This is important because we still need to find critical chi squared. To find critical chi squared, we need to find our degrees of freedom. This is a mathematical thing. It's basically the number of categories minus 1. This is our second formula. There's 4 of these highlighted formulas. We'll get to them. Basically, orange and white, right? Those are our 2 categories. So our degrees of freedom is 1. So remember in our table, we had orange, white, total, observed, and expected. 2 categories. 2 minus 1 is 1. The other thing we need to have in order to find our critical chi-squared is alpha. Biologists and scientists around the world have agreed upon a standard alpha. It's the same we had for the t-test, 0.05. So this is 5% error. Totally standard. Every person who's part of the scientific community goes with this. There are some very extreme examples where we don't, but typically we do. So alpha. So this symbol is alpha. Often it's drawn like this as well. It's another Greek letter. So 0.05. You just have to memorize it. It comes up a lot. So now to find critical chi-squared, we found calculated chi-squared by using a calculator and a calculation. We calculated chi-squared. Critical chi-squared comes from a critical table of values, like this. Once upon a time, in a land far, far away, mathematicians of old did the math. They made this table. So now we don't have to do this. We just look up the critical value on this table. So we need to know which row to use and which column. I like to do column first because it always stays the same. Our column is always 0.05. This to me is the cutoff line. Everything on this side of that cutoff line, we're going to accept our HO. Everything is the same. But if we cross this critical threshold, everything on this side, we're going to reject our HO. Things are different over here. But we need to know which number in this column to use. That's where our degrees of freedom comes. So our degrees of freedom is 1. So we're going to be using 3.841. That's our critical cutoff point. If our calculated chi-squared is less than that, we're going to accept HO. If our calculated chi-squared is greater than that, we're going to reject HO. So our critical chi-squared, 3.841. And this is what I was just saying. So if 3.841 is our critical, if our calculated is less than 3.841, we're going to accept, and if our calculated is greater than, we're going to reject. Our calculated chi-squared is 0.5. That is less than 3.841. So we're going to accept our HO. There is no difference. What is there no difference between, though? That's where a concluding statement comes in. There is no difference in the number of species of orange butterflies versus the number of species of white butterflies on the west coast of North America. If our calculated chi-square had been greater than our critical chi-square, then we would have accepted our HO and we would have used this concluding statement. But because our calculated was less than, we accepted our HO and used this. So calculated chi-squared less than critical chi-squared, we accept HO. And there is no difference. Down here, if calculated chi-squared is greater than critical chi-squared, then we reject HO. And there is a difference. This just takes practice to remember this part, or looking it up, or memorizing it. But that's it. That's the whole thing. You now know how to do a one-dimensional chi-squared equation. If you found that whole presentation a little overwhelming, let's practice. Let's do a second example. This time we're going to look at the butterflies in eastern North America. So same null hypothesis. There is no difference between the number of orange species of butterfly and the number of white species of butterfly, except this time we're looking at eastern North America. So if we count our orange butterflies, we have 18, and if we count our white butterflies, we only have 6 this time. That seems like a bigger difference. So let's see if it's statistically a bigger difference. So how we do this is first we need our null hypothesis. There is no difference in the number of species of orange butterflies and the number of species of white butterflies in eastern North America. And then let's do an alternate hypothesis as well, just to practice. Realistically, just the opposite of the first sentence. Then we need to make our table. So we had 18 orange butterflies and 6 white, which gives us a total of 24. Now you remember our expected is the total divided by the number of categories. So we have 2 categories, orange and white. So 24 divided by 2 equals 12. So that's why we have these 2 expected values. Once we have these, we can calculate chi-squared. So chi-squared equals the sum of observed minus expected squared over expected. So we only have 2 pairs of numbers, so we're going to add this together twice. Observed minus expected squared plus observed minus expected squared. Both of these need to be over expected. I forgot that part. 18 minus 12 squared over 12 plus 6 minus 12 squared over 12. 18 minus 12 is 6 squared And 6 minus 12 is negative 6 squared. 6 squared is 32. I'm going to go this way because I need the space on the bottom. 6 squared is 32. No, 36. And 36 divided by 12 is 3. 3 plus 3 equals 6. Calculate chi-squared of 6. Now we need to find our degrees of freedom. So that's our number of categories minus 1. We have 2 categories. So our degrees of freedom is 1. If our degrees of freedom is 1 and our alpha is 0.05, we're going to be the same place on our critical table of values as last time, right? So it's that same 3.841. Which means we reject HO. Our calculated chi-squared is 6, and our critical chi-squared is 3.841. 6 is greater than 3.841. So we reject our HO. Our calculated chi-square has crossed that critical threshold. We're rejecting HO. So that means our final statement is that there is a difference because we rejected HO. On our last example, we looked at orange versus white, and they weren't different. They were the same. This time, they are different. There's enough of a difference there. There are fewer whites statistically than orange. Last time, they were pretty much the same statistically. Okay, we're going to do this one more time. This time we're going to look at Central North America, and we're going to do orange versus blue. We have 16 orange and 11 blue. A lot more blue in Central North America, I feel. So again, there is no difference in the number of species of orange butterflies and the number of species of blue butterflies in Central North America. So very similar. We've changed the color and we've changed the location. So it's orange and blue, and it's in Central North America. Our alternate is the opposite of our null. So we've got our table. So again, our expected is the number of categories, so 2 categories. So 27 divided by 2 equals 13.5. That's our expected value. So to find our calculated chi-squared, we have 16 minus 13.5 squared over 13.5 plus, right? The sum of means plus 11 minus 13.5 squared. (16 minus 13.5 is 2.5 squared over 13.5. And 11 minus 13.5 is negative 2.5 squared over 13.5. And squaring it gets rid of those negatives. So this is 6.25. And again, I'm going to go this way because I need that bottom space, but usually you'd keep going down. I like to keep my rows nice and neat. 6.25 divided by 13.5, 0.463. And that gets us 0.926. What did I write? Yeah! Calculate chi-squared equals 0.926. Our degrees of freedom is 1 because we have 2 categories, so 2 minus 1. Our alpha is always 0.05, which means our critical chi-squared is still 3.841. Anytime your degrees of freedom is 1, your critical chi-squared is going to be in the same place. We need to do an example that has more than 2 categories. So it means we're going to accept HO, right? For the same reason. If our calculated chi-squared equals 0.926 and our critical chi-squared equals 3.841, our calculated is less than our critical. So our calculated chi-square hasn't crossed that critical threshold. So we accept HO, everything's the same. There is no difference. So there's no difference between the number of orange and the number of blue butterflies. Oh, I just noticed this says white. It should say blue. Hopefully, after a few examples, you're starting to get the hang of this. Go and try 2-dimensional chi-squared now.